Hello, this video is going to take a look at calculating the kinetically stored energy inside of an object. Once again, if you have not looked at the video of basic energy types, you may want to go back and take a look at those just to make sure that you have kind of a background on the different types of energy storage. Once again, the kinetically stored energy means the object has to be moving. And our formula for calculating that, the kinetic amount of kinetic energy in an object, once again measured in joules, is the fraction 1/2, or as a decimal, right, 0.5. So since I'll be using the calculator, right, I will be using the decimal 0.5, but it is just the fraction 1/2 times the mass of the object times the velocity squared. So once again, all of these things are just multiplied together. So once again, m equals the mass in kilograms. And once again, just to make these problems easy, I'll probably always give you the mass in kilograms. The v is the velocity or the speed, the direction of this doesn't really matter, so we can just say it's speed in meters per second. Once again, if I was interested in having you do practice with conversions, I'd give you miles per hour and have you convert or some such. But in this unit, we're more looking at, can you calculate the amount of energy and the interchange between kinetically stored energy and gravitationally stored energy. So I won't be worrying about the unit conversion so much in this unit. So I will probably already give you the mass in kilograms and the velocity in meters per second, and we'll just work through from there. So once again, I have a car in 4 different positions here. Going 4 different velocities, so this car is continually speeding up. Right, the arrows, the way we do most of our diagrams, represent the speed of the object. These are kind of drawn proportionally. I kind of ran out of room with the last arrow, but from here to here, the velocity is twice as much. From the initial to 30, it's 3 times larger, and from the initial to the last, it is 4 times larger. So one of the questions that we asked on some assessments are, if it does have twice the velocity, right, what happens with the amount of kinetically stored energy? And your first impulse might be to say it is twice as much, but I think we'll find out with the numbers that is not quite the case. And so then we will go back and take a look at that here momentarily, and we'll see how that works. To do all of this, though, we do need the mass of the objects. We need the mass of a car. So we'll just say that a nice kind of round, easy number to use that's still kind of realistic might be about 1,000 kilograms. That might actually be a little bit small for some cars, but we'll go with it for the moment. We'll assume it's a little larger than a smart car anyhow. So for the kinetic energy at 10 meters per second, it is 1/2 times 1,000, and I'm just going to not write the units in with this, times 10 squared, or just to make it a little more compact as I'm writing it, but it's 1/2 times 1,000 kilograms times 10 meters per second, and that is all squared. Now, a couple of things with the math with this. I'm just thinking with the algebra and the way it works, that there's some things that people do, like they multiply everything and then square it, or they multiply the half times this, and then the half times the 10, and then square things. But I just like to split it into 2 pieces. The first thing I do is take half of the mass, or 0.5 times 1,000, and that would give you 500. Just write that number down, and then square just the velocity. It is always just the velocity that is squared. So it's 10 squared, which means 10 times 10. And on your calculator, that would give you 100. And then the last step is just to multiply those 2 numbers together. I know with algebraically, it's like one extra step. You can put it all in a calculator and just multiply it one after the other if you know how to do that. But just to get rid of a lot of the confusion that sometimes happens, I would actually break the problem into two portions like this, and then multiply, and we'll get 50,000 joules of energy. All right, so that is the algebra for that. If we're doing 20 meters per second, it is the same sort of thing, only now it's 1/2 of 1,000 times 20 squared. So once again, I will just break this into 500 times 400, which should give me 200,000 joules of energy. So we find out if we double the speed, it is not double the energy. In fact, if we're looking proportionally at the change, right, what we can do is we can take our second energy and divide by the first one. And I'm just going to do that so we can just see kind of a proportional change here. And if we do that, we actually get the number 4, which means this number is 4 times bigger than that number. So if we double the velocity, we don't have twice the energy, we have 4 times the energy. And you possibly have already figured out why that happens, but let me do one more. Actually, let me do both of these other problems, and I'll do kind of the same proportional thing. Keep going back to the initial. We're going to use this 10 meters per second, and the 50,000 joules is kind of our base to compare to, and then I think maybe you'll see the pattern. Right, it was a little bit easier to maybe see a pattern inside of the gravitationally stored energy. This is from a different video, right? Things are just proportional. If you're halfway down, it is half as much, and that all works out. It's a little bit trickier with the velocity and the kinetically stored energy. But let me just work through the other two examples on this practice real quick. This is half of 1,000 times 30 squared, which is 500 times 900, which is 450,000 joules. We'll see these numbers get quite large quite quickly, which is back when we were talking about momentum more with collisions. But this is one reason why it is really, really hard to design even airbags and seatbelts and things to completely protect passengers going at high rates of speed, because the energy gets significantly larger. Right? If we have 3 times the velocity, we now have 9 times the energy. And before long, there is so much energy when we're increasing our speed that it is hard to somehow dissipate all that energy safely, even to the people inside of the car. And so let me do our last little quick calculation here. 1,000 times 40 squared, which is 500 times 1,600, which is 800,000 joules. So as I said, we find out that things go very, very, very large very, very quickly. And once again, let me divide that from the original 800,000 joules. 50,000 joules is 16. So, do you see the pattern yet? Right. This is twice as much, the energy is 4 times as much. If the velocity is 3 times as much, the energy is 9 times larger. And if the velocity is 4 times larger, the energy is 16 times larger. All right? And the way that works is the proportions are squared. When the velocity is twice as much, the energy is 4 times bigger. 3 times for the velocity, 9 times bigger, 4 times the velocity, 16 times bigger, and that comes from this squared factor on the velocity. All right, 2 squared is 4, 3 squared is 9, 4 squared is 16. So that is the way that it works. I think from here, we wouldn't even probably need to do all these rest of these calculations. If I said we had the same car at 50 meters per second and said, what would the amount of kinetically stored energy be? It would be 5 squared, or 25 times the original. So we take 25 times the original amount of energy. And if we said 8 times the velocity, 8 squared is 64, so it'd be 64 times the original energy. And so we can work these problems that way also. So we don't have to keep using the same equation over and over again if you know proportionally what is going to happen. And the way the kinetically stored energy does work is proportionally the energy does change like the square of the velocity. So if we don't have these kinds of problems to work, and we just want to know how much kinetically stored energy there is in some random object, if we know the mass and the velocity, we do just use the formula. Right, if there is some sort of a nice pattern with the velocities and you can figure out proportion what happens, you can use the proportions also. But in either case, this is the relationship. To find the kinetically stored energy, it is 1/2 times the mass times the velocity squared. Thanks for watching.